Okay, so for this question, what you need to memorize is in an acid, methyl orange becomes red, and in a base, it becomes yellow. So when you're titrating a base to an acid, the moment the base becomes an excess, it becomes yellow. Any hydroxide is basic, ammonia is a basic gas. You don't want any acid left in the end, so it has to be limiting. The reason filtration is because magnesium oxide is insoluble, but magnesium nitrate is soluble. So that's the way you separate. Again, we took it before, like the first time we took filtration, how you separate sand and salt water by filtration, because sand is insoluble. A solution in which no more solid or solute can dissolve at that temperature is called a saturated solution. If I have a salt water solution at that specific temperature, if I add any more salt and it doesn't dissolve, it just stays a solid and it sinks to the bottom, it's saturated. A cold glass rod is dipped from time to time in the solution to check the formation of crystals on the tip of the rod. Again, if it's saturated, the crystals are going to form around because the temperature changed. So that means when the temperature increases, more dissolves. But when the temperature decreases, less dissolves. So that means the solid already inside the solute already inside would solidify. So when the temperature around the glass rod becomes colder, it's going to solidify around the glass rod. In step 7, it says he dried it with filter paper. This is the most common and most probably the safest way, because the only danger you have here is crushing them. If you dry them too hard, you can crush them and turn them into powder. Here, this is the problem if you try it with heating. If you overheat them, or if the temperature is too high, the water will be lost too quickly. Here, it's with an acid and a base. For a soluble salt, here it's to get an insoluble salt. You're trying to get a soluble salt, so that won't work. And here it's the only one left, and here it says base magnesium oxide. Any metal oxide is basic, that's why it says addition of excess base. And the way you could tell which acid it is by the anion in the salt you're trying to get. So you're trying to get magnesium chloride, so that means Cl. The only acid Cl is HCl. Here's how you read the equation. You just have to balance it. It's already basically balanced for you. You just have to remember that Mg is Mg2 plus and Cl is Cl minus. That's why it's MgCl2. Here, Kw is already given, but you still have to memorize it. At 25 degrees Celsius, this is how it is. The pH of anything is pH equals negative log 10 of H plus. That means that H plus is going to be 10 to the negative pH. This you should already know. This you should know it. It's really useful. 10 to the negative pH is equals to H plus, or 1 times 10 to the negative pH. It doesn't matter. So that means here the pH is 5.36. So H plus equals 10 to the negative 5.36. And we know Kw equals H plus times OH minus, concentration of both. We already have the concentration of 2 and we're trying to find the concentration of OH minus. So if you replace everything we already have, so that means 10 to the negative 14 equals 10 to the negative 5.36 times OH minus, and if you just divide both sides by 10 to the negative 5.36, you get the answer. Put it on the calculator, because if you try it on paper, this is what you're gonna get. You're gonna get 10 times 10 to the positive 5.36. You're gonna get like 10 to the power of 8 point something something something. It's like when you get a decimal as your exponent, you have to, there's like a lot of rationalization. So if you just put it on the calculator instantly, and then here three significant figures. In the next question, you're gonna see that when you get the pH here, like it might be, you guys are gonna think it's gonna be wrong what I said when like pH, that the concentration of H plus is 10 to a negative pH. See here, because they're different. I'll explain it now, because if you put again on the calculator, you're gonna see what I mean. So a student is asked to find the pH of a solution. In experiment, he prepares aqueous solution of hydrochloric acid, HCl, dissolving 0.08 moles in 250 milliliters volumetric like in a 250 milliliter volumetric flask, filled up to the calibration mark 25 degrees Celsius. So this gives you H plus Cl minus. These two are in a 1-to-1 ratio. 1:1. So that means the concentration of this, C of this, is going to be equal to the C of this. We already know that C equals N over V. They gave us the N, 0.08 moles, so 0.08, and they gave us the V, 250 milliliters. But the thing is, in chemistry, it's always going to be in decimeters cubed. It's never going to be in another unit for volume, unless the answer is in the same volume. But the SI unit in chemistry is this one. In physics, it's this one. You have to remember the difference. Decimeters cubed is the same as liter. So the way you get from milliliter to liter, divide by 1,000. Divide by 1,000. So that means the V, so N equals 0.08, V equals 0.25. So then you just divide them. This is the answer you get. You get 0.32, but you want it in 3 significant figures. For this one, the pH is negative log 10 of H. Put this on the calculator, and then look. So you put on your calculator, if you have the CW, you have to specify 10 at the bottom. So you go negative log 10. In the bracket, you put 0.32. This is what you get. The reason I said, you guys, because I said in the last question, H is equal to 10 to a negative pH. If you put 10 to the negative 4.95 on your calculator, you're gonna get 4.95, my bad. If you put 10 to a negative 0.495 on your calculator, you're gonna get 0.319, which is 0.32. This is basically the same thing, but you have to always check the ratios. It's basic stoichiometry. See here it says H2A, H2. This is the main thing. So you H2A gives you H plus A. We don't know what A is. It's at a 2-to-1 ratio. So whatever you get here, you're gonna have to double. So here, this is 0.4. So X. We don't know it yet. So they gave us a concentration here. This is a concentration, this is a concentration. And look here in this question, they're gonna confuse you. They're gonna say 298 K. It's basically the same as 25 degrees Celsius. You have to memorize that KW is equal to this at 25 degrees Celsius, or 298 K. Cross multiply. Yeah, cross multiply 2x equals 0.4. No, wait. Whatever, they're gonna... The concentrations, the only difference here is that this is double of this. As the moment. So, if this is gonna be 0.4, this is gonna have to be My bad, I got it wrong. So you have to balance. It's gonna be 2H. So it's the other way around. So this is gonna be 1. This is gonna be 2. 0.4 x. Cross multiply. You're gonna get 2 times 0.4 equals to x, which is 0.8, as the answer says here. And then again, Kw equals H plus times OH minus. So that means that OH minus equals to Kw over H plus. It's given to you here what Kw is, so that means OH minus equals to 10 to the negative 14 over 0.8. You're gonna get 1.25 times 10 to the negative 14, which is exactly what they gave you here. Again, see 25, they want hydrogen ions in an aqueous solution of KOH. So that means KOH gave out K plus OH minus. So that way, the way you get OH minus is, again, it's at a 1-to-1 ratio. KOH gives K plus OH minus. See, 1-to-1. So whatever the concentration here is going to be here. So again, the concentration is 0.6. And again, we're going to use the same thing. Kw equals to H plus O times OH minus. So that means that H plus is going to be equal to Kw over concentration of OH minus. So 10 to the negative 14 over 0.06. If you put it on the calculator, this is the answer you should get. Yeah, it's the answer you got. So again, they wanted 2 significant figures this time, not 3. Always read the question how many significant figures they want. Whenever you have an acid added to a carbonate, which is CO3, CO3 2 minus, you get a salt plus water like any other, but the only difference is plus CO2 gas. It always happens. So that's why here it says there's a formation of bubbles, because you got a gas. The bubbles give you a gas. Net ionic equation is with the stuff that cancels out. I don't know if I have enough space. I'll try. H plus Cl minus. I'll show you everything that cancels out. Plus Ca2 plus CO3 2 minus. Oh no, wait. It's a solid. CaCO3 gives you, splits up, becomes, again, it gives you a salt. Salt here would be CaCl. CaCl2, which is aqueous. So Ca2 plus Cl minus plus CO2 plus H2O. Here you see we just have to add the 2 here, and that's it. See? So here it's balanced, because your 3 O's, 2H, 2H. This can cancel out with this. So this is again, and then this cancels out with this. So in the end, your final net ionic reaction would be H plus CO3 2 minus gives you H2O plus CO2, and they're asking only for the products. So these are the answers. Anything less than 7 is acidic. Anything more is basic by a certain level. Not like 7.1 is going to be basic or 6.9 is going to be acidic. But see, the way they help you here a lot with the colors. You can kind of tell which is basic, which is acidic. But 7 is right in the middle, it's neutral. So here it's less than 7, so it's acidic. At 7, so it's neutral. More, so it's basic. Another word for basic, I don't know if they're gonna give it in the exam, is alkaline. Oxides, here's the main things you have to remember. Anything metal oxide is basic. There's three different exceptions, which are the amphoteric ones. So metal oxide is basic. But the non-metal one is acidic. Non-metal oxide is acidic. Except for you have a few exceptions which are neutral. So here see, Mg is a metal, so it's going to be basic. C is a non-metal, so it's going to be acidic. Copper is a metal, so it's going to be basic. This is one of the exceptions. Again, you have to memorize N2O is neutral, but NO2 is acidic because it's a non-metal. You have to remember that. CO again is neutral. You have to remember that. CO2 is acidic. CO is neutral. Zinc oxide is amphoteric. It's one of the exceptions. Same with aluminum here. This one, Ca is a metal, so it's basic, and S is a non-metal, so it's acidic. Schrödinger line is not an acid. Acid, not all the time. Usually, the way you can tell them is they start with H. H2SO4, HCl. Another example is HNO3. Usually, most of the time, they start with an H. That's an easy way to tell. But this one, the way you can tell, this is a metal carbonate, CO3. It's not. There is a carbonic acid, but it doesn't. This is a metal carbonate. Again, you can tell also by the one before it. Carbonic acid is. There is carbonic acid. I think it's H2CO3. And KOH. Anything most of the time. Anything that ends with OH is basic. It's a hydroxide. Needed titration. Titration, you have the flask which has you have the flask which has either the base or the acid, the burette for the titrate, and then the pipette to you need the pipette to measure how much exactly. This is the only one with the flask. You need the flask. That's the whole point of titration, where you're putting. The titration kind of looks like this. You have the burette here. Just forget the drawing. You have the burette here into a flask here. You're kind of dropping into it. You need a flask. You can't just drop into the air. Red litmus paper, blue. Remember question 2, it was asking which are bases. Ammonia, or NH3, is a basic gas. It's litmus paper turns red in an acid and blue in a base. And ammonia is also really known for having a pungent smell. Urine has a lot of ammonia, that's why it has a really strong smell. Ammonia and ammonium are different. Ammonium is NH4, so NH4 plus. So an acid or a base, sorry, because ammonium is a weak acid. This weak acid. You have to remember that. So ammonium salt plus a base gives you NH3 gas plus a salt plus water. So the salt here would CaSO4, I think. The water here, and the ammonia gas is released. During the preparation of silver iodide by precipitation, what is the order? You see here silver iodide. Remember, halides are soluble with everything except for Ag+, Cu+, and Pb2+. So this is why precipitation is used, because it's insoluble. The first thing is you mix the two solutions. You have two aqueous solutions. One of them has Ag. Here you have two solutions. This one has Ag something. We don't know what the something is. It's not important. And this one has something I, because I is the anion here. You have to mix both of them. That's the first step. Second step is you mix them. So then you stir them. So they mix well. So here, see? So now it's AgI, and then the other solid we don't know. But the other solid is soluble. Again, it's soluble. Because, like, let's say for example it's AgNO3 nitrate, which is soluble with everything. And you could put like NaI if you want, anything. So we don't know what it is. It could be literally any substance, but it's soluble. So the way you get, again, an insoluble solid from a soluble mixture, like a mixture with already a soluble solid inside, you filtrate, and then again you dry the rest in an oven or by heating, like we said before. But it has to be really the reason it takes a lot of time, because it has to be like, if it's too high heat, again it's gonna happen what happened in I think it was question 4. Which of the following reagents can be added to sulfuric acid to prepare copper sulfate? Now you're gonna need to remember this. Copper, usually copper alone, not even 2+, copper and silver are usually way too weak to react with anything, to react with acids. They basically just give negligible stuff. That's why everything here is picked except copper. Copper is too weak. Like the reaction is so weak, it's basically negligible. If they react with an acid, that's what happens. That's why everything else happens. Because again, it's not just copper, so the other stuff doesn't make it negligible. It can't, like, here copper with an acid is weak. It doesn't give you anything. It's way too weak. But a metal oxide on the other hand is different. A metal carbonate is different. A metal hydroxide is different. Which of the following reactions produce a gas? Strong acid, an acid and a base. Acid and a base give you salt plus H2O. Ammonium salt plus base gives you NH3 plus salt plus water, like we said before with the ammonium. Acid and metal carbonate give you salt plus water plus CO2 gas. The way you can usually tell sometimes if a gas is given out is dependent on the substance. Like here you see ammonium gives you ammonia, a carbonate which is CO3 gives you CO2. Acid and a metal oxide, the reason this one doesn't work, even though I just said usually with a gas how it works, is because a metal oxide again acts as a base. It basically acts exactly like a base. Sulfite is different than sulfate. Sulfite gives you sulfite is SO3 2-. It gives you SO2. And also there's sulfide. There's 3 of them. There's sulfate, sulfite, and there's also sulfide. So this one is SO4 2-. All of them are 2-. This one is SO3 2-. This one is just S 2-. sulfide, the S2 minus, when it reacts with anything, the sulfide when it reacts with anything gives you a salt and H2S gas. Which of the following reagents can be added to hydrochloric acid to prepare zinc chloride? Again, it's called ZnSO4. SO4 is soluble, and also SO4 isn't like, SO4 doesn't really react. It's because it's not acidic, and it's not doesn't react with anything really that much. It's soluble. A strong electrolyte exclusively gives ions. That means mainly gives ions, or only gives ions. Like most acids are strong electrolytes. Most ions are strong. A weak electrolyte to ions only to a limited extent. That means it gives some ions, but not a lot. Like the other one gives, just completely dissolves into ions. This one dissolves, but only some ions are given, not a lot. These are present in any aqueous solution. The way it works is because aqueous literally means dissolved in water. So H2O, when you react something in H2O, breaks up into H plus OH minus. That's why it's in everything. That's how everything has a pH. Again, the way you can tell is most of the time, not all the time, most of the time something that starts with H is an acid. And here a metal oxide is basic. Best method to obtain crystallization, again, H2S, because okay, look, this is an acid, this is amphoteric, so it can act as both acid and the base if you need it to. If it acts as the base, gives you this. They're both soluble in the end. Because you're gonna get H2O, and the zinc, you're gonna get H2O and then zinc sulfate. So since they're both soluble, H2O is water, it's already dissolved, so the way you get a soluble salt is through crystallization. To prepare PbSO4 salt, equal quantities of PbNO3 and Na2SO4 are mixed in water. Yeah, okay, look, you want to get a reaction that in the end is gonna be you want to get a reaction that one of them is gonna be soluble and the other is. That's why most of the time you're gonna see them with NO3, because NO3 is soluble with everything. And the reason this one works is because, remember, SO4 has exceptions, has 4 exceptions: capacitor, calcium, barium, strontium, and lead. The insoluble salts are prepared by precipitation. That's how we do precipitation. You're trying to get soluble salt in the end. Progressive addition of a base to an acid is called titration. Again, remember, it's you have the burette up here, and it's pouring slowly into the beaker. Usually, most of the time, this is the base and this is the acid. Goes one drop at a time into the acid. So and the way we can tell is an indicator. That's what question 1 was about. Because the way you can tell when to stop adding is through an indicator. Like methyl orange, for example. As soon as it turns yellow, that means the base is in excess. Wet litmus paper is red in acid and blue in basic. This one you have to memorize. This one, all of the indicators are just memorization. Which of the following color of phenolphthalein in basic? This is another. There's 4 indicators. There's 4 indicators that we have to memorize. It's this one, phenolphthalein, plus I might spell it wrong. Thymolphthalein plus you have the litmus, plus, and the last one is methyl orange. So look, there's a table I have. I'll just write all the letters because I don't have enough space. So you have acid and in base. P, okay, you have P, T, phenolphthalein, thymolphthalein, litmus, and methyl orange, MO. So in an acid, this one is colorless, and this one is colorless, and these two are red, red, red. In a base, this is pink, this is blue, this one is blue also, and this one is yellow. The way you can memorize them is just P, P. This one just memorize litmus also, but most of the time the ones that do make up a color in an acid are red, like these two. And the way you memorize this one is orange, is red and yellow. Drag and drop the first terms. Equation that determines the volume of a base added from the burette used in an acid to base titration. So again, yeah, it's just last reading of the burette minus first reading of the burette. Again, because the burette is made in a way where basically it's like, usually you have at the top the biggest number and at the small the biggest one. But a burette kind of works differently, where it's the opposite. Here on the top it's gonna be 0, and at the bottom is gonna be the biggest number. So let's say I started here at 20 and I ended up at 45. The way I can tell how much I use is I just check the difference. Again, this one is memorizing. So here, see, in a base, methyl orange is yellow, and in an acid it's red. The way you memorize is again red and yellow make orange. So formula you have to memorize it. This is how you get the pH when you have a concentration of H+. 25 degrees Celsius. pH of pure water is 7. Water is completely neutral. Again, 7 is neutral. Water is neutral. pH paper used to measure the approximate value of the pH of a given solution. It's not exact. The pH paper isn't usually exact because there's no decimals, and the color you kind of have to like the color isn't gonna be 100% clear. This is Bronsted-Lowry's definition. Yeah, Bronsted. So you have two definitions. You have Bronsted-Lowry and Arrhenius. Bronsted-Lowry said that an acid is a proton donor. The reason he said proton is because H plus is made like this. Look, H plus is only one proton. You should know this. So it's a single proton in the middle, and because H plus there's no usually it's like this. H gas is just like this, but H plus you don't have the proton, you don't have the electron, my bad. So it's just one proton. So that's why here they say one proton instead of, like here was why they say a proton donor instead of, like, for example, a hydrogen donor. Arrhenius' definition, forgot to mention, Arrhenius' definition says that an acid is something in something that releases H plus in water, and a base is something that releases OH minus in water. The reason this works is because if you see, for example, an acid like HCl, it gives away the H to become water. Like you have HCl plus NaOH. It gives away the H to become water. So there's two H's in total now. But the reason a base is a proton acceptor is because it's OH minus. So NaOH again plus HCl, the OH takes the H and it becomes water, H2O. When KOH is added, yeah, because hydroxides or OH minus aren't soluble with everything, or insoluble with everything except for group 1 NH4 plus, H plus, and barium and strontium. It's insoluble with everything else. So that's why when you add them, this is insoluble. Yeah, okay. So you already know it's an acid. When an acid acts with a metal, it gives you hydrogen gas and the salt. When it reacts with a carbonate, it gives you carbon dioxide, salt and water. And when it acts with a metal oxide or a base, gives you salt and water. The way you can tell which acid specifically is because here you see copper oxide gives copper chloride, so HCl. That's a CQD question. Anyways, if the burette was filled with dilute hydrochloric acid and the solution was slowly added to a conical flask containing dilute sodium hydroxide solution, what will the color change in the conical flask if the following indicators are added? Choose the correct answer. Again, you have to remember which one it is. So this time, usually the acid is in the flask. Usually there's an acid in the flask. So usually there's a base in the burette and an acid in the flask. But here they're telling you the opposite. So here's the acid, and then down here in the thing is the base. See? Here's the base. So whatever indicator you add here, let's say you add litmus, it's gonna be blue. And then when the acid becomes excess, when you know when to stop is when it becomes red. That's it. So if the burette was filled with dilute hydrochloric acid, the solution was slowly added to a flask containing sodium hydroxide. Hydroxide is a base. So here again, these are just memorization. So, but it's the opposite. You have to always read the question like really well. So here the burette was with the acid. So look, let's say you added this one. It goes from blue when it's in the base, and then when there's enough acid inside, it becomes red. And then methyl orange, yellow to red, and then thermophthalein. It's blue in a base and colorless in an acid. Anything that ends with, like the two we have that end with phthalene, they're colorless in the acid. A reaction of a strong acid with a strong base to produce salt and water is called neutralization. This one's memorization. You're basically neutralizing both of them. That's why it's called that. You're making it, when you do it, when you add an acid with a base, you get water, which is neutral. It's just a way to remember it. So here, choose the correct answer to complete the following. Solution X is acidic because the pH is less than 7. And again, you remember I'll show you now this one you have to remember it. Okay, pH, concentration of H plus, concentration of H plus equals to 10 to the power of negative of the pH. So the pH here is 4, so that means hydrogen is 10 to the power of 4. And then again, Kw is always 1 times 10 to the negative 14, so that means 10 to the negative 14 equals to 10 to the negative 4 times OH minus. Then here's just, you put on the calculator, or it's just easy.